All right, good morning, everyone. Please let me know if you are able to see my screen. Uh, just a moment. All right, thank you. Sorry, I did not, I forgot to unmute you. All right, thank you. Okay, so we were discussing energy-based models last time, and we discussed quite a bit about energy-based models, and we um, basically came up with the concept of contrastive divergence. All right. But what I would like to do today, I mean, before I move any further with this particular topic, I would like to spend some time on some important concepts in energy-based model, just to make sure that you all intuitively understand, and as well in terms of intuitive and mathematically also, you understand that why we need these kind of energy-based models. Because I mean, if we talk about autoregressive models, if we talk about variational autoencoder, if we talk about normalizing flow models, if we talk about GAN, we know exactly why we needed this kind of models. Here, we know that we need this kind of models because we are not able to calculate the normalization constant, which is the denominator. But that is not enough. There has to be some other concepts that needs to be clear. Okay, so let's let's start going through it. Just a moment. Let's start going through it. Okay. All right. So the first thing that you need to understand here is, I mean, what exactly are, when we are saying energy-based models, what exactly do we mean by that? Okay. So the first key concept here is essentially an energy-based model defines a scalar energy function. Okay. And the way we will write it as E theta, it's a function, energy function, E theta, which is x, and it belongs to real numbers. Okay. And where essentially x is a configuration. Correct. X is a configuration. It can be anything. It can be a data point. It can be a visible state. Right. It can be a visible hidden pair, like we saw in Ishing's model. All right. Etc. Okay. And theta, what are model parameters? Okay. Now, note one important thing here. This model, EBM, okay, EBM, I mean, this energy function, okay, this model does not define probability directly. Okay, it does not define probability directly. Instead, probability is derived from this. Okay, so basically, instead, probability is derived from energy. Okay, now, and I'll explain you why we need this particular approach. Okay, so key thing to note here is that EBM defines a scalar function. It will give you a scalar energy function. So it will give you a scalar output, okay, which takes X and gives a real number. And this function and has theta as its model parameters, and it does not define a probability distribution directly. We will get the probability distribution, and basically we'll derive the probability distribution from this energy function. Key concept here. Okay. Now, second concept that you need to keep in mind is how do we go from probability? How do we go from energy to probability? So from energy to probability. Okay. And we essentially go via something which is called the Gibbs distribution. Okay. And we have already studied all these things in the last class. I just want to put all the pieces together so that the mind map is clear for you. Okay. So this Gibbs distribution is also called the Boltzmann distribution, from which the restricted Boltzmann machines and the deep Boltzmann machine came. Okay. So EBMs use essentially Gibbs distribution or the Boltzmann distribution. The Boltzmann distribution is represented like this. And now you can relate to the last class. This is E, right? And Z theta. This is the form of the Boltzmann distribution. And as you know, Z theta is nothing but the partition function. And this partition function, you can write it like this. Okay. Or this is the continuous case. And if it is discrete, it will be sum. Okay. This is for continuous. And essentially, what happens is this essentially ensures the normalization. This essentially ensures the normalization. So a few crucial properties here that you need to remember, and we talked about it last time, is that why are we using this form? Why are we using this form, e to the power minus e theta x? We are using this form because because of positivity. Okay, so essentially e to the power minus e theta x will always be greater than 0 for all x. Okay, so probability will always be positive. Okay, now what is the other important thing that we want to do here? The other important property is called the order reversing monotonicity. Okay, what do we mean by that? So what we mean by that is, and now things will start getting intuitively clear for you. So let's say we have two states, x1 and x2. And we say that the energy at x1 is less than the energy at x2. Okay. And from all your high school statistical physics or physics knowledge and all those things we have talked about last time as well. When I mean, everything in this universe is in a kind of state of equilibrium. Okay. And if it is in a state of equilibrium, as per statistical physics, it has been shown that they are in low energy state, because that's where the stability comes from. Okay. So what we want to say here is that the energy of this particular of x1 is less than the energy of x2. Okay. And the way in which we use this particular thing is that if the energy is less, if the energy of x1 is less than the energy of x2, it means that the probability of x1 is greater than the probability of x2, the reverse one, the reverse. All right. So what exactly do we mean by that? What we mean is most of the things in this world are in equilibrium. Okay. And when the things are in equilibrium, obviously the probability of finding that particular state in equilibrium is much more than to find it in a state of non-equilibrium or a high energy state. Okay. This essentially means that if we relate this concept to statistical physics, that essentially means low energy equal to high probability and high energy is equal to low probability. That is the thing. So somehow, when we are using this energy function, we need to use it in such a manner that 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 when we find the probability, when we derive the probability from these energy functions, uh, the probability or should be reversed. It means that the probability of x1 should be greater than the probability of x2. And if you just mathematically see this particular thing, what happens here is that e to the power minus e x1 will be greater than e to the power minus e x2, which implies that the probability of x1 is greater than probability of x2. And if you just take a toy example here, I'll just take a toy example here. So let's say 1 is greater than 3. And this is basically your energy. 1 is less than 3. So what will happen? Minus 1 is greater than minus 3, right? It reverses. And if you put in this, e to the power minus 1 is greater than e to the power minus 3. So low energy state have high probability. Okay, so that is the reason why. So the first reason we have used exponential is because of that thing that we talked about, positivity. The second reason is because uh, uh, I mean, not only the exponential, but e to the power minus theta x, the functional form that we are taking is because to get this particular property, which is basically the order reversing monotonicity, so that a low energy state equal to high probability and a high energy state is equal to low probability. Okay. Now, the third property that we are interested in is additive and something called the additive energies. Okay. And additive energies means multiplicative probability. What do we mean by that? So it means that if energy decomposes, we can write it like this, decomposition. And if we take this functional form, we can write it like this. Now you see what has happened. We can write it like this, right? So what has happened? The additive energies is equal to the multiplicative probability now, you see. All right. So this mirrors the log probability additivity. Okay. So this is essentially one other property, because ultimately when you are doing when you are calculating the likelihood, what do you have? You have probability of x1, probability of x1, probability of x2, probability of it's basically the product of the conditional probabilities, right? We are always interested in the product, not the sum. So to move from that particular state, from the additive energies to the multiplicative probability, this is the right kind of function that we use. So the key, the moral of the story here that you should always remember is essentially you have this energy function, E of x, you make it into this particular form, this, you add normalization, and you get your P of x. This is the entire mapping. Okay. Now, this is the mathematical part of why, how we use energy, how we correlate energy and probability. Low energy state is equal to high probability state and vice versa. But now the next logical question that should pop up in your mind is, why do we even need energy instead of probability? We were all throughout the 11 lectures or 10 lectures at least, we were always discussing about probabilities. Now, why do we even need energy instead of probability? Now, that is a key question that we need to answer, because we know this is an energy-based model. We know this, that, this, but why do we need it? Why did people like Jeffrey Hinton and all those people all chase this kind of models? Okay. Now, the key thing to note here is that this is point number 2. The point number 3 here is that the question that we need to ask is, why do we even need energy instead of probability? Okay. Key question. Now, what happens? What are the two things that this energy and probability answer? Okay. Energy will answer what looks good or bad. And your probability will answer how often. How often exactly? Two perspective of looking at things. Energy says whether the state is good or bad. Probability says how often this state occurs. What is the frequency of occurring this particular state? Okay. Two different ways of looking at the state. All right. So what probability forces you to do? Now, if you have a probability distribution, if you model a probability distribution, now let's talk about 3A. Let's talk about probability a little bit. Okay. If you want to model, if we want to model a probability distribution. Okay. If we want to model a probability distribution directly, how do we go about it? The first thing that we need to do is assign a non-negative number to every possible x. So assign a non-negative number to every possible x. Okay. The second thing that you need to do is everything sums or integrates to 1. That's a key property. And third, what we need to do is compute the normalization constantly. Okay. These are the three things that you have to do when you want to model a probability distribution. Now, what happens is in high dimensions, the first thing is the space of X, okay? The space of X is astronomically large. Number two, normalization is expensive or intractable. And third point that we have is we must actually decide the exact densities. All right. So, I mean, even when we know about the relative plausibility. So essentially, we must know the exact densities. Okay. What is the meaning of the third point? The meaning of the third point is that to calculate probability, you must, we must know the exact densities. Even though we may know that x1 is better than x2, but to calculate it exactly, to calculate the exact, we must know the exact densities to calculate the, um, to model the distribution. Okay. Simply knowing x1 is better than x2 will not help. To model the distribution, we have to know the exact densities. And because of this particular fact, many a times, this is an overkill. Okay. This is an overkill. Now, the question is that what, how does, uh, what does, what benefit does energy give us from this perspective? The benefit that energy gives us is, so what energy lets us do instead? The thing that energy gives is energy function will answer the question, only answer a simple question. Is it good or bad? It's a comparative analysis. Okay. And not basically how often X occurs globally. Okay. Sorry, how often X occurs globally. Okay. Or what fraction of the total mass does it get? Okay. And now you see a particular trend happening here. When we are talking about from an energy perspective, it's a much more simpler approach. We are saying that x1 is better than x2, x2 is worse than x1. We don't want to know how often x1 occurs globally, what fraction of the total mass x1, x1 has, and what fraction of the total mass x2 has. Right? Much more simpler approach. You don't have to deal with all these things. It's a different way of looking at your data or your configuration or your states. All right. It's a totally different way of looking at your states. Okay. Now, the key thing here is that and what you need to remember, is, EBMs, models geometry and not frequencies. Okay. Now, what do we mean by that? EBM says that, EBM basically shapes the energy landscape. Okay. So just from a technical standpoint, EBM shapes okay. And what do we mean by that? It means that data lives in valleys, and we'll discuss it. Okay. Implausible regions are mountains. And just visually try to think about it. You have a you have a landscape where data lives in the valleys. Implausible regions are the mountains. Okay. And what has happened? Learning essentially deepens the valleys around the data. Okay. So we are not memorizing the frequency, but the learning structure. And this is why EBMs excel at multimodal distributions. So why are we saying that the data lives in valleys? Because you remember that probability and energy are have a inverse probability. Now, when we are uh, um, going after a probability distribution, let's say a multimodal Gaussian or something, the modes of the Gaussian will be obviously the higher part of the bell curves. And however, in case of energy-based models, what is going to happen? All your data will live in the valleys, okay? And the implausible regions are basically the mountains, okay? And why this matters during training? Why this matters during training? Because during training, we will try to push the data downhill so that it goes into the valleys and push the non-data or the noise or anything uphill. So this creates a separation, and basically without ever needing explicit labels or probabilities. So that is the entire concept of why we need and why we are using the functional form that we talked about here. The functional form that we talked about is not only about this, it is about why we are using this approach. Why we are using this approach? It is just a different perspective and a much easier perspective. Okay, so that is the whole reason why we are using energy-based models. Okay, any questions?
So you
Oh,
mentioned valley and hill, no? So
hmm.
what does it represent? Is it low energy or high energy state, something
Yeah,
like?
yeah, yeah. So just think about it. Okay, I am showing you. So this is your multimodal probability distribution, right? Hmm. Now, what will happen is this is your probability distribution. And if you simply inverse it, E of X, what is going to happen? This is going to become like this, right? So
Yes, sir.
so this is what we are saying essentially, because it's the inverse relationship. So it says that all the data lives in the valleys and all the, non-data sort of things, they live in the mountains.
Okay, sir. Thank you.
All right. So one thing I would like, let me see. Okay. So one thing, I think there are 20 people here. One thing I would like you to remember from this particular 30 minutes lecture today is there are a lot of times when we study about energy based. See, when we were studying autoregressive models, when we were studying variational autoencoder, when we were studying normalizing flow models, we intuitively we understood why we did that particular thing. But the sometimes what happens is with energy based models, you will get the mathematical definition, you will get everything, but you will have a difficult time getting your head around in terms of why this perspective has been used. And this is an important thing that you should, these 30 minutes are important for you to remember, because energy based models are also the foundation for diffusion models and a few other things. So it is important for you to understand that this notion of energy based models has been taken to basically get a workaround around all the constraints that we have in and working with probability distributions and other stuff. Okay. All right. So now where do you where, okay. So now we have talked a lot about all these things. Okay. So last time we were in this particular slide, which was contrastive divergence. And contrastive divergence was a way for training what we call energy-based models. Now, the key problem with contrastive divergence is everything looks good, but how do we sample from an EBM? Okay. And you understand why it is difficult to sample from an EBM? Because we don't know this. Okay. So how do we sample? How do we sample from an uh, EBM? And that is the key question, because if you are not able to, you know your training data, you have your model, everything you have found out a way so that you don't have to calculate your z theta and all those particular things. But now in this particular thing, it is saying that you have to sample from your EBM. But how do you sample from EBM? Because we cannot sample. Now, how do we get around this particular thing? This is the thing that we are going to discuss now. Okay. All right. So before we discuss this particular thing, and any of you have, I mean, how many of you know about MCMC, Markov chain Monte Carlo sampling? I mean, any of you, I mean, know about it? Um, I'll anyway give a refresher, but that's fine.
And 27 and 33 and 34. I don't understand lots of things in maths, but I'll show you.
There are 0, 1, 0, tens and 0 hundreds.
Hmm?
There are 0 ones, 0 tens and 0 hundreds.
Okay. So the key thing here, when we are, so what we need to do is we need to do to basically sample from an EVM, sorry, EVM. What we need to do is we need to do a Markov chain Monte Carlo sampling. Okay, Markov chain in Monte Carlo sampling. Now, you know about sampling. We have random sampling, we have accept reject sampling, importance sampling, all those stuff, right? So Markov chain Monte Carlo sampling is one sampling technique. And typically why we don't use accept reject sampling or random sampling is because they are inefficient. Okay. So what do we do? So the first thing in this particular aspect is there are three concepts. Okay, one is the first concept is Markov chain, and I know you all have studied about it. I'll just give a quick uh, refresher. So what is a Markov chain? Markov chain is nothing, but it is a mechanism that helps you move around the space. Okay, so let's say you have this state, you want to go to this state, you want to go to this state, and so on, so forth. And obviously, every state will have a transition probability, that is probability of xt plus 1 given xt. So what Markov chain does is uh, Markov chain in just basically um, is the mechanism that moves around the space. It is the mechanism that moves around the space. Okay. And in fact, it is not this as well. This is wrong. This is basically the mechanism that moves around the space. Okay. By itself, it does nothing. When you go from one transition from one state to another and you create a chain, and Markov chain just represents how you move around that particular chain. Now, what happens is uh, now typically when we say Markov chain means that you just remember the previous state. When you go to the next state, you just remember the current state. So unlike here, we don't have this. And so on. No, we don't do this. So Markov chain tells that the next state is going to be dependent on the current state. Okay, so the memory is just one state prior. And this is basically a one Markov chain, and there are 2, 3 Markov chains as well. But when we say Markov chain, we typically mean one Markov chain. Okay. Now, the second concept here is something called a stationary distribution. What do we mean by a stationary distribution? Now, what happens is when you, uh, I mean, when you go via the Markov chain, when you have not Markov chain, but any chain, when you have a chain of events or chain of states, all right, what happens is stationary distribution basically describes where the chain spends its time in the long run. So when you have a long chain, stationary distribution will describe where the chain spends its time. So it describes where the chain spends its time. Okay, and not only where the chain spends its time, but where the chain spends its time in long run, because the chain will not converge. Okay, so what Markov chain what Markov chain is saying that what stationary distribution is saying that essentially this probability distribution this is arrow, right? Not negative. Yes. So it is saying that when you move ultimately what will happen is when you transition from one state to another, your distribution will remain the same. And then that's what and that's where we say we have reached a stationary distribution. And why do we want to reach a stationary distribution? The reason why we want to reach a stationary distribution is because if we reach a stationary distribution, and if, for example, and this pi is nothing but this probability, okay, just for to remove the confusion, I'm putting it as probability. So now if we reach a stationary distribution for an EBM, what will happen is your probability of X will be proportional to S. Okay, so distribution your distribution is going to mimic your true distribution, probability distribution. Okay, your probability distribution. So Markov chain is nothing but it is a mechanism that moves around the space. Typically, Markov chain in Markov chain, we just remember the current state for going to the next state. And my ultimate goal, this is the goal. Okay, my ultimate goal is to reach a stationary distribution. And why do we want to reach a stationary distribution? Because when I reach a stationary distribution and I move from one state to another, my distribution will never change. Okay. And the stationary distribution, the final stationary distribution will mimic this functional form. And why do we need it? Now just think about one particular thing. Now suppose I know the probability distribution and I tell you to do sampling from there. I mean, you will be easily be able to do that because you know the functional form of the distribution, right? However, if I don't know the functional form of the distribution and probability distribution, and I put a bound on it or something, and I try to do some sort of sampling, it is very difficult for me to do efficient sampling from there because many of the points will lie outside the distribution. Okay, so what we do here is we want to have a mechanism which takes us to the goal of finding a stationary distribution which mimics the energy-based models. And when I have reached that stationary distribution, if I have some mechanism to do sampling, then my job is done. I have sampled from there. So the way it happens is the third component is called the Monte Carlo. Okay. Third component is called the Monte Carlo, Markov chain Monte Carlo sampling. And this is basically the actual sampling. Okay. Now remember, Monte Carlo is is um, uh, essentially an umbrella of sampling activities. Okay, an umbrella of sampling activities. Monte Carlo has the basic Monte Carlo form. It has essentially your Metropolis Hastings, Gibbs sampling. All these are various flavors of Monte Carlo sampling, but we'll not boil the ocean and we'll not go there. Okay, so what happens is, what does Monte Carlo sampling do? So Monte Carlo sampling is basically the construction rule. Okay, what is meant by that? So you had a Markov chain. Markov chain is what? It is just moving around in the space. What was the ultimate goal. The ultimate goal was to reach a stationary distribution. How do you go from one? Now, Monte Carlo sampling will give you the construction rule from going from one state to another in such a manner that you reach that stationary distribution. Okay, so Monte Carlo sampling is not the chain itself, it's the construction rule. Okay, and it tells you basically, it helps you basically define transition properties. Transition properties. Okay. Now, what do we now? How do we go about it? Now let's go back. Let's go back to our this. Okay. Yeah. So this is the slide. All right. So this is the subsequent slide where we wanted to sample, but we said, how do we sample from this? So we sample from this using Markov chain Monte Carlo. All right. Now, in Markov chain Monte Carlo, what is going to happen is I'll show you the exact flavor. This is a very primitive form. All right. So you initialize your x theta randomly at t is equal to 0. So essentially means that you start with any state. So you are going from one state to another. You start with any state. Right? You start with any state. And what I do is when I basically, let's say this is x0. When I come to x1, how do I go to x1? I go to x1 by adding some noise, and this can be Gaussian noise as well. Okay, I just add some noise to the current sample, and I basically try to go to the next step. And how does it help? It helps because you know the energy function, you know the functional form of the energy, right? You know the functional form of the energy function. So let's say the energy function is like this. Okay, and you start from here. So this is your x0. What you are going to do is you are going to determine a step size, and you are going to add some noise. And after adding noise, what is going to happen is you are going to pass it to the energy function, and you are going to check whether the energy of this or this is more. Okay, the energy of this or this is more. All right, and the way in which you move forward is, if you see that your next sample is better, then you move towards it. Now this becomes your x1. Now this becomes your x1. All right, now again you add some noise to this. Okay, and now maybe this time maybe you add some noise and you go in the different direction, which is this. All right, now what will happen is, obviously logic says that you should stay in the current position because the next position has a lower plausibility than the current position. Okay, but there is a certain trick that is applied. The trick is that we generate a random number between 0 and 1. Okay, so every time, so now remember one thing. If your f of theta xt plus 1, this particular ratio will always be greater than 1 when essentially your future state, your next state is better than the current state. But if your next state is worse than the current state, then this will be less than 1. In less than 1, we should ideally not move forward. Okay, we should keep the current state. But instead, what we do is we generate to introduce some stochasticity, or randomness. What we do is we generate a number from 0 to 1, any random number from 0 to 1. If that random number is less than this ratio, okay, then we basically keep it here. I mean, we basically keep the same state. If it is more than the ratio, then we basically move to the next state. How does it help? It helps because what is going to happen is, let's say you have this kind of distribution. Okay, and let's say you start somewhere from here. Okay, what is going to happen is you are going to take small steps by some noise perturbation. Okay, and you are going to move from here to here, here to here, here to here, here to here, without any stochasticity. Now, once you reach here, obviously, the next steps will always go downhill, should always go downhill, and you will never take those steps because their ratio will always be less, and you will you will now think that you have reached the best possible position. Okay. Now, what happens in this particular case? You have not explored the entire distribution or entire space. To prevent this particular thing and to help in exploration, what we do is we add that kind of stochasticity or randomness. And when we add that kind of stochasticity or randomness, what happens is it always takes the uphill move, but at certain times it also takes the downhill. And if it takes the downhill move, then basically it starts exploring the space. And that is how you basically um, do the Monte Carlo sampling. Okay. And what happens actually practically in Monte Carlo sampling is you take thousands of samples. Okay. It's a random walk like this. Okay. You take thousands, each point here is a sample. So you do random walk here, and ultimately what will happen is you will see that when you have explored the entire space, you will see that you have reached a stationary distribution, and that stationary distribution will mimic your energy-based distribution and energy function. And essentially, you now are able to sample. When you are sampling here, they are all good samples. Okay, it has a burnout. It has a burn-in phase, which is this, which when you do it practically, you ignore that particular phase and you take samples from here and you get this. So this is basically MCMC sampling, which we use to basically sample from EVMs without the necessity of knowing the normalization constant. Okay, so now if I come here, okay, so what is written works in theory, but can take a very long time to converge because thousands of samples you have to pick, very long time to converge. Okay, so what else can we do? We can and basically take the help of a score function. Now let me talk about the score function, and it's a very important concept, score function, and because it will help in your uh, diffusion models as well. Okay, so what is the story till now? The story till now is EVM is just a different way to look at probability distributions. In high dimensional space, it is often not practically possible to work with probability distributions. Sometimes we don't even need to calculate the actual density. We just need a comparative analysis. Probability, you doing comparative analysis with probability distribution needs access to the probability densities, which we will not have because that partition function is essentially intractable or very computationally expensive. So we take the help of energy function, and energy function essentially helps us to basically model the distribution and take a comparative look at it, whether it is good or bad. And contrastive divergence was one of the ways to train this kind of models. However, there was problem in that. I mean, we needed to sample from that model. We cannot sample from that kind of model because we don't know the partition. So we used the MCMC technique. The MCMC technique is nothing but the Markov chain Monte Carlo technique. Three components to it. You have the Markov chain, which is nothing but how you move around in the state space. Okay. And you have the ultimate goal, which is the stationary distribution. Stationary distribution in this case is your energy function. All right. And the way we move around in the Markov chain is being dictated by any form of Monte Carlo um, uh, sampling. Okay. And we studied the vanilla form of Monte Carlo sampling, and which basically, when you do thousands of steps in this Monte Carlo sampling, you will reach the stationary distribution. And that way you are able to sample from the distribution. But as shown in the earlier slide, this particular takes very long time to converge, and it is not an ideal way to train, because when you are training your model, you need quick access to the samples. If your sampling itself takes a long time, then your learning will go for a toss. Okay, so that brings us to the next important thing, which is called the score matching or the score function, and we will go through it. Okay, so all right, so let's do one thing. Let's take a 10-minute break. This was quite intensive. Let's take a 10-minute break. We will catch up at it's 37, right? We'll catch up at around 47, all right, 11:47. All right, so let's get started. Okay, so now what we saw is MCMC sampling, MCMC technique is not a good way to sample. Is there any better way to sample? And that brings us to the next part, which is called score matching. TCHING. Right? Now, score matching is now we need to remember that there are three layers here. The first layer is your energy, which is E theta x. The next layer is your unnormalized density. Which is given by f of theta is equal to exponential of minus E theta x. Okay. And the third layer is your actual probability or normalized probability, which is given by E theta x is equal to f theta x z theta. Z theta. Okay. Now, nothing to get confused about. What we have done is, instead of writing this exponential form, we have just wrote it in a compressed form, which is basically which will represent the output of the neural network. Okay, f theta x is nothing but the output of the neural network. Okay, now what can we do here? So the primary form here is this. We can take the log of both sides. What will happen? This. Okay. So now, what does the left-hand side represent? It is the log. It is basically the likelihood. Okay, I mean log likelihood. Okay. Now, if we take the derivative of this entire thing with respect to x, what is going to happen? So we take the derivative with respect to x and we say log of p theta x is equal to derivative of x log of f theta x minus derivative of x log of z theta. All right. And this is a derivative with respect to x. There is no x here. This is a constant. So this will be 0. Okay. So what has this form showed us? That this form has showed us that the log gradient of the likelihood is equal to the log gradient of the neural network, which implies that this of this is equal to this, which means that if we are able to somehow take the gradient of this log, gradient of the log of this energy function I mean, not the energy function, but the entire unnormalized, what you call the energy function. And so what is going to happen is it is going to be it is going to be similar to our to the actual probability distribution. Okay. And this particular term here is called the Stein score function, or simply the score function. And what does it show? It shows that, and how this is useful basically. Okay. So it means that if we align them everywhere, the probability distribution will be equal. Okay. It means that this is P. Okay. It means that your P of this will align with this. Okay. Very nice property. And the only way, I mean, the topology of both the things would be same. And the only way this topology can and differ is like this, which is basically the log. There is no other way in which it can differ. And this by a constant k. So now what we can do is we can say that essentially okay, which implies right, if we take the integral of both sides, which implies this is equal to 1, which implies e to the power k is equal to 1, which implies that this does not have any impact. All right. So the core thing that we have understood from here is that the problem with MCMC was not only it took a large amount of iterations to get a single sample. I mean, to get us to basically get to the stationary distribution. All right. So it converged. It took a lot of iterations to converge. The another key problem with MCMC was that uh, I mean we kind of blindly added some noise there just to check the distribution of whether the next step is better than the current step or worse than the current step. So we added some noise, we added some stochastic noise, and we said that whether the next step is better than the current step. All right. We did not use uh, any kind of intuitive, I mean, any kind of mechanism, any kind of scientific mechanism. So we said we add some noise and see whether the ratio is good or bad, and then we take that particular step. Here, what we would be doing is we would be essentially following that score function, which is basically the gradient of the log, uh, the gradient of the log likelihood. The gradient of the gradient of the log likelihood. All right. So this is essentially, a much nicer way to follow the gradients. All right. So now where do we go from here? Let's see which slide I was in. So this is the same thing. All right. So that brings us to the next sampling technique, which is called this Longevin MCMC. All right. Now, Longevin MCMC is essentially also called the unadjusted Longevin dynamics. All right. And we will study when we are studying the what you call the score-based models. What we'll see is we will go through the adjusted Longevin dynamics, which is much more nice. All right. But let's start going through the unadjusted Longevin dynamics, right? In the unadjusted Longevin dynamics, what happens is, okay, let me see. So this is the next sampling technique. Okay, the technique is called unadjusted Longevin dynamics, right? Or Longevin MCMC, whatever you want to call it. So what we do here is that we take an initial sample from any proposal distribution. All right. So what we'll do is we take an initial sample from any proposal distribution. So this is basically the proposal distribution. So take all right. And then what you do is you repeat for all time step. Okay. For all time steps. Now here, what we are going to do is, so this is just to start the Longevin, in this X0 is just to start the Longevin dynamics. All right. Or Longevin sampling. So what we are going to do is, this is step 1, this is step 2, this is 2A. 2A is going to be sample noise from a Gaussian. All right. And we'll say ZT and identical distribution. Okay. And now what we do is we get a new per trap sample. Okay. On noisy sample. This particular sample, this particular sample will work in this particular manner. So X t plus 1, or let me write it in the next slide so that we have more space. X t plus 1 is equal to xt. And let me write down the equation and then I'll explain it. This is the form of the Longevin in sampling. All right. So what Langevin sampling is saying is, you take your previous step, and initially it was x0, and then what you do is you go in the direction that should increase the probability of the sample p theta. Okay, so go in the direction which would increase the probability of the sample p theta by following the gradient, and obviously gradient with respect to x. All right, and this epsilon that you see here is basically is the step size. All right, it's a step size, and there is a certain ratio in which the step needs to be made. I mean, step size of, I mean, certain ratio in which the step size of the gradient and the noise has to be scaled to make it work. All right, so this is kind of empirical. Okay, so what what are these? So this, we have said that the Z we have sampled from it's some noisy sample, and we scale. What we do is we add some noise as we do not want to be greedy and explore the space. Same thing as I showed you in the normal vanilla MCMC. Okay, so we want to explore the space. We just don't want to follow the gradient. We want to explore the entire space. All right, and that is the reason why we put um, we put I mean, we had some noise here, and what this is saying, this entire thing is saying is that, and remember, this is nothing but a form of noisy gradient ascent. Okay, and what this technique is saying is that take a sample xt, follow the gradient, and add a little bit of Gaussian noise, and we should be able to sample better. And it is better than the previous technique because in that particular thing, we were blindly making changes earlier by adding some small noise and trying to see whether it is better. But here we are following the gradient, which is a much more informed decision. All right. So this is the second method, which is called the unadjusted Langevin dynamics. And let me see where exactly. So this is the unadjusted form of unadjusted Langevin dynamics. And now let's move forward. Okay. All right. So all these things we have discussed. All right. Unadjusted Langevin dynamics we have discussed. Okay. And so now goal even that we can find which will not involve sampling. If we are able to not sample from the model, then our problem is solved. We don't need to do MCMC and we don't need to do unadjusted Langevin dynamics and all those particular stuff. Is there any mechanism in which we can basically train the model without sampling from the EBM. Okay. And that brings us to the score function, which I showed you. All right. And this is the visual representation of the score function. If you see, these are the these are the basically the areas where low density areas. These are the high density areas. That is the bell curves or the modes. All right. And you can see that the gradient moves in this particular direction. So this is nothing. This is nothing but a vector field. All right. This is nothing but a this is nothing but a this is nothing but a vector field. Okay. And I mean, uh, gradient with respect to x tells us how the probability change when we change the sample a little bit. Okay, that's the key. That's the key idea. And you can see that these are the score matching. These are the forms of score matching. All right. So your S theta x provides an alternative view, essentially, where we are looking at things from the perspective of the gradient instead of the perspective of the likelihood. So that's the key story. So we are now looking in things from the perspective of the gradient instead of the perspective of the uh, likelihood. Okay. So let's move here. So now you see that obviously we saw that this is your score function. This was your score function, and this is independent of the z theta because your z theta got cancelled out when you took the gradient, and I mean it moved to 0. All right. So that brings us to one key objective here when you are using score matching is this, which is called the Fisher's divergence. Fisher's divergence has this particular this optimization has this particular form, which is essentially your half of your expectation of x with p of gradient of x log of px minus gradient of x log of qx, and it's a n to naught. Okay. And now what it is trying to say is that this is the loss. This is basically nothing but the loss function. All right. This is basically nothing but the loss function. And what it is saying is that if two distributions are similar, their vector fields also has to be similar. Okay. Now, this is the form. This is the, I mean, score matching, minimizing the Fisher divergence between the P of data and the EBM. Essentially, that is our scope. And this is the form of this. Now, but the problem here is that we have access to the samples from P data. Okay. But the actual distribution is not known. And that is the same problem. That is P of data is not known, and hence the quantity cannot be calculated. And if we actually knew the P data, then we never had to do any generative modeling. Then we could have basically essentially taken. I mean, we could have directly drawn the samples. Okay. Now, what do we do? Can we come to a functional form where we don't have to basically know P of data? Okay. And that brings us to this particular thing, which is essentially just a mathematical derivation. Don't need to worry too much about it, but it just says that what it is saying, you take this particular functional form, how to deal with this particular log of p data x given only samples. All right. You basically integrate by parts. All right. And an univariate case has been taken so that it can be explained well. And now here the derivation has been done. So this has been so you have taken the functional form of this, and the functional form, all the expectations has been expanded like this. All right. The expectation has been expanded here, the integral of p data x. And now what has done is the entire expression has been expanded, and we have three what you call parts to it. Okay. Three parts to it. The first part is this. Okay. The first part is this. It does not have any theta. All right. It does not have any theta, and hence essentially it can be ignored. All right. And this particular part here, this particular part here is essentially depends only on the model. Okay, it does not depend on your p data distribution. Yes, there is an integral of p data x. This is nothing but the expectation, and when you are doing expectation, you just need the samples, you don't need p of data. Okay, so we should be good with it. This red part is the one which is basically the culprit. Okay, because here you have the gradient of log of p data, which is difficult to calculate. So what we do is we use the high school calculus, which is integration of by parts. And when you do the integration of by parts, you essentially get to a point where you get this particular functional form. Okay. And this particular functional form, if you see, has no p of data in it. That integral of p data is nothing but the expectation, but there is no p data. So it is saying that integral of p data x and the double derivative of log of p theta x dx. All right. And so what we have done is we have mathematically taken the help of high school calculus, and we have uh, I mean we have done some mathematical trickery on the Fisher's divergence, functional form of Fisher's divergence, and brought it to a form which is essentially which no longer depends upon your P of data. And yes, it depends on the samples from P of data, which is there in our training set, but we don't need the exact density. All right. And now here, I mean, if you see now what has happened. So this is the final univariate form of score matching, which is this. All right. And nowhere there is P of data, and we are all good on this particular front. And you don't need to know this, but still, if you using a multivariate score matching, what is going to happen? It is going to be a little bit more tricky. This particular thing here, I mean, is going to be replaced by the trace of a Hessian, and trace of a Hessian will return a scalar. So we should be all good. But yes, it is a little bit complicated. Okay. So now how the score matching algorithm works? The score matching algorithm works like this. Sample a mini batch of data points. Okay. Sample a mini batch of data points x1, x2, xn, which belongs to p data x. Estimate the score matching loss using empirical mean. And so now nowhere there is p of data. You do essentially stochastic gradient descent, and there is no need for sample from EBM. Okay, and obviously the caveat is computing the trace of Hessian in general is very expensive for large models. Okay, so this is one technique. This is one technique where you don't need to sample from your EBM. The other thing is the other thing which you can do is this particular thing, which is called the noise contrastive estimation. All right, which is called the noise contrastive estimation. Now, let me just take a few blank pages to explain you. Okay, so what we would be discussing now is essentially your noise contrastive estimation, right? So it's an important technique. It is also called NCE. Okay. Now, obviously, what is an NCE? NCE, like score matching, is a parameter estimation technique for unnormalized probabilistic model, right? Now, what is the core? What is the core idea? The core idea is that convert density estimation into a binary classification problem. Okay, convert density estimation instead of into a binary classification problem. So what we are going to do is, instead of directly maximizing likelihood, what NC is going to do is train a model to distinguish real samples from the artificially generated noise samples, something similar to GAN. Okay, so what we are going to have is, we have data samples and we have noise samples. Okay, and obviously this noise sample, this distribution of noise sample has to be a simple distribution from which we can actually sample. If it is a complex distribution from which we cannot sample, then there is no point of using this algorithm. Okay, so this model will learn the parameters in such a manner that the data samples are more likely than the noise samples. And if your model says that your data samples are more likely, than the noise samples, that means that that is the underlying distribution. Okay. So what is the key intuition here is that if your model assigns high scores to real data and low scores to noise, all right, then the thing that you must think about is that it must be close to the true distribution, even if it is unnormalized. Okay. And the learning question is this sample real or noise? And instead of asking what is the exact probability of the sample. So we are saying this is the same way we talked about right at the beginning of the class, a different way of looking at it. We are saying, is it real or is it noise? Okay. And the setup is like this. Okay. And the setup is like this. So this is the unnormalized, you all know, model score. For example, we took this form. Okay. And you will know that this is basically the partition function. And then P of nx is the known, this is the key thing, known noise distribution. All right, it's known, otherwise you cannot sample. Okay. And K is basically the number of noise sampled. It's basically nothing but a batch. All right. We can ignore this as well. Number of noise samples per data sample. nothing but the batch. All right. So what we need to do is we need to basically define the posterior probability that a sample is real data. All right. And we can basically do this in this particular manner. So this is the posterior probability of D is equal to 1 given X. What does it mean? It means real data. Posterior probability of real data. And posterior probability of real data is given like this. Okay. And the other thing is P of D is equal to 0 given X, which is equal to K P of N X okay. And what does the objective function now becomes? Now NCA maximizes the likelihood of correct classification. All right. So NCA maximizes the log likelihood of correct classification. So your log likelihood of NCE is equal to expectation of P data log, all right, of f theta x plus k p of n x plus k e p of n, and the same thing comes here log k. In many literature you will see that k getting ignored, but that's fine. I mean, either way it works, right? So f theta x plus k p of n x this. Now note one thing, and I'll show you later. This is exactly the logistic regression between data and noise. Okay, and I'll show you why we are saying this. And why it works is essentially as k tends to infinity, your f of theta x tends to p data x up to a normalization constant. Okay. Now, the key thing to note here is that no partition function is required. So, I mean, Z is either absorbed, you can either absorb Z in the parameter, all right, or I mean, you can learn it explicitly, all right. And obviously, you get a flavor of what we saw in contrastive divergence. You get a flavor here. It is contrastive learning by comparison. Okay. And obviously, what you need is a good noise distribution. The only problem of this particular method is that you need a good noise distribution. If your noise distribution is far off from your true distribution, then you lose the signal, because ultimately it's a logistic regression curve. And if you are on the right at the tail of the logistic regression curve, I mean bottom of the logistic regression curve, you will not get any gradient and signals. And if you don't get any gradient signals, how do? So this is one problem. All right. And so what happens is, now you see that NC turns essentially density estimation into a binary classification on problem, right? And why we say that this is essentially looking like this is essentially nothing but what you call uh, logistic regression. So the reason why we say that this is logistic regression is because of the following. All right. So if you see here, now what we know here is probability of data is equal to 1 given x is equal to f of theta x divided by f of theta x plus k p of n x. All right. And I can write it in this particular form, which is 1 by 1 plus k p of n x f of theta x, and I can write it in this particular form, which is 1 plus e to the power minus log f of theta x k p of n x. All right. And ultimately, what you see is that this has taken the form of a sigmoid function or a logistic regression function. All right. So this is essentially contrastive contrastive what you call um, uh, sampling. Noise contrastive sampling. And this is essentially the slides about noise contrastive sampling. And if you go through this, and this is essentially the logic. The logic is the same. You do a mini batch from data point, mini batch from sample, and then you use this particular functional form. Note that this particular functional form has a log sum. Log sum it has because, I mean, they have converted this particular thing for numerical stability into a log sum. You don't need to know this, but if you are interested, you can go through this. And the key difference between an NC and a GAN is both involves training a discriminator to perform binary classification with the cross entropy loss. Both are likelihood free. And differences is GAN requires adversarial training. That is, we do min-max optimization. NC does not do min-max optimization because your generator is fixed. All right. NC requires likelihood of the noise distribution for training, and while GAN only requires efficient sampling from the prior. Right. And NC trains an energy-based model, while GAN trains a deterministic sample generator. Right. So this is the comparison between NC and GAN. So this is essentially the more or less the machinery of energy-based models. Now, any questions on this? The key thing that you all should remember is, I mean, all this mathematics is fine unless and until you decide to do some research in this particular field. You don't need to boil the ocean. But the key thing that you need to understand is, why are we using energy-based models? Okay, we already know that we can calculate via likelihood, we can do maximum likelihood estimation, we can do likelihood free training using GAN. But what is the need for another type of model, which is energy based model? And the first 30 minutes of the lecture is exactly going to give you nail the intuition in terms of why these energy based models are needed. If you are clear in your mind why these energy-based models are needed, then you will not get confused of what is the energy, what is probability, why are we comparing it with statistical physics and all those particular thing. The only thing is that the entire concept has been derived from statistical physics, because in statistical physics, things have a high probability of living in lower energy states in equilibrium, and That is the entire concept that has been and brought in here, and it gives us a different perspective of looking at things, and specially helps you not to do expensive computation or something, not to not only computation, but some of the things are intractable. So you don't need to work with probability. You can work with energy functions, which helps you compare two unnormalized probability distributions. And sometimes that comparison between two distributions is enough to do your learning and train the model. So that is the entire concept. Okay. All right then. So let's close the discussion for today, and next session, and I'll start with what you call diffusion models. Thank you.